Thanks a lot. Yeah, my name is Simon Zeder. I'm from Fluxim, and I'll continue a bit more actually on optical modeling, as we heard already before, especially about our recent progress for modeling of photon recycling and luminescent coupling phenomena in here specifically perovskite-silicon tandems. I also want to thank my coworkers Beat Steller and Urs Eberhardt, who will also have a talk in the afternoon. Okay. It's continuing on my laptop, but not on the slides. Interesting. Okay. There we go. Okay, just a very short motivation why we're actually working on this modeling. I think I don't have to talk a lot about perovskite-silicon tandems, since we all know what it is, but I think it's worth mentioning that we all hopefully agree that those are very promising devices for future electricity generation for low cost and high efficiency solar cells. And also I just want to give a quick shout out to my colleagues at the PV Lab in Neuchâtel, who recently achieved 2 new world records with exactly these devices, with efficiencies above 30% for flat end textures. Now, why are we looking at this these phenomena of photon recycling and luminescent coupling? Well, we all know that perovskites, ideally, they have a very high radiative efficiency and a high overlap of absorption and emission spectra with itself, and of course also with the silicon subcell. And exactly, these two together lead to these photon recycling and luminescent coupling effects, of which actually also quite a significant amount was measured in these record devices. Now, also since these are purely internal phenomena, it is very hard to assess experimentally. So modeling can help to assess the impact of these phenomena. So as I said, start already with the optical models, what we are using. Since we are looking at tandems, we're looking at the optical multiscale problem for emission, but also for absorption and the coupling of those two. On the one hand, we have the perovskite subcell, which is on the order of hundreds of nanometers, so we need to employ like wave optical models, transfer matrix models, basically solving Maxwell's equations. But I mean, that's not really how our solar cell looks like, right? Basically, it's silicon. And for such thick layers, we actually cannot really employ wave optical models anymore, so it's more appropriate to look at light intensities, ray optical models. So how do we actually tackle this? So for the coherent light in our device, we use a Green's function approach to describe the electromagnetic fields. And actually this approach is quite powerful, since with this Green's function here, we can calculate many different quantities, so like an emission rate, spatially, spectrally, the resulting reabsorption rate in our coherent substack, also of course the power flux, so the Poynting vector, which will actually be more important also later on. So basically this is the coherent part, right? Now for the incoherent part, we need to use a different approach. Basically what we use is this net radiation model, it's called, where we basically just take the fluxes at each interface and we relate them to one another through the interface transmittance and reflectance. This can either be just directly calculated from the 2 layers next to them, if they're incoherent, or also through transfer matrix characteristics of the coherent substack, if the interface basically consists of, for example, the perovskite subcell. Again, here we can calculate emission rates. Since we are here the optically homogeneous medium, we can just use the normal von Rosberg-Shockley rate. From the resulting fluxes of our net radiation model, we can calculate this reabsorption rate, and so on. Now, of course, those 2 regimes, they're not independent from one another, right? They talk to each other. And as I already mentioned, the main coupling quantity is this time average Poynting vector, which kind of relates the intensity to the coherent electromagnetic fields, right? You can have emission from the coherent substack, which enters the incoherent layers, is absorbed, is reflected, moves back into the coherent substack, and so on. Now, the entire details are a bit annoying, so I think I won't go really into the math of how to couple these 2 regimes. But, I mean, obviously it's possible and it works, so you just have to believe me on that. Now, we are not only in the optical regime, right? We are having a solar cell, so we also have electronic characteristics. And for this aspect, at the moment we use the diffusion model, which is implemented in ZFOS, obviously, since I'm from Fluxim, which is coupled to these optical models. In this case study now of this Tandem device, we have, for example, the recombination, which consists of a bimolecular radiative term, chocolate reed Hall and Auger recombination. Generation is just the external illumination and the reabsorption, where you see in blue the quantities which are actually impacted by our optical model. Now also, since we are having a Tandem device, we need to model somehow the recombination junction, for which we use here at the moment a chocolate reed Hall type of interface recombination mediated through trap states and parameterized by these interface recombination velocities. So just a very quick case study that I wanted to simulate from a discussion actually back at the Tandem PV workshop, where someone asked me if we could actually simulate an easy way how to kind of measure the luminescent coupling. So basically what you do is you take your Tandem device. Here I put on a thicker perovskite, which you'll see later. Then you just shine high energy light on it. So what do you expect? Of course, you would expect all of your light is absorbed in your top cell. And this is indeed what we see also from our optical models. Now, if we don't have any luminescent coupling, right, all your generated charges in the top cell, they have to recombine. They cannot move, since in the silicon you don't have any generation. So your current is basically zero. Now, what happens if we actually look at if we include luminescent coupling? Basically, your perovskite kind of acts like a down conversion filter, and you indeed get some generation in your silicon. And this you can actually also see then at your terminals as a current flowing through your device, which, if you look here, so about 14 milliamps per square centimeter, which, if we integrate these generation rates, is indeed what we have as a luminescent coupling from your perovskite to your silicon bottom cell. Now, of course, this is also not as simple as it might seem. Like, the type of recombination that you have in both of your cells are affecting, of course, the current that you can measure. So it might not always be as easy as it looks in simulation. But now, okay, let's move on to the actual device. Usually here we want the current matching. So our perovskite now is thinner. It's about 300 nanometers. And what we can already do just optically is a kind of optical loss analysis of your internal radiation. So basically we can look at where is our internal emission going. And actually for this device we already see it's quite efficient. Like about 45% of the internally emitted light is reabsorbed in the perovskite, and about 52% is actually transferred into the silicon. And only very marginal amounts are lost to parasitic absorption or to outcoupling. Now also, again, as I said, we also want to look at the electronic characteristics. Of course, the first thing we do is simulate the JV curve, where we have the optically filtered subcells, the silicon, the perovskite, and the full Tandem. And we see already that the junction is very good. We don't really have a big voltage loss from the subcells to the Tandem. Now, maybe I should mention the solid lines here, always neglecting any effect of reabsorption, with the dashed lines including these effects. Now looking at the actual Tandem JV in the, let's say, interesting region of MPP and VOC, we see a bit more details. Of course, your performance increases if you also consider these reabsorption effects. And here in blue you have the radiative limit, and in orange you have including chocolate reed Hall. Of course, performance is worse if you include chocolate reed Hall effects. As you can see, for both cases, we have a VOC enhancement due to this reabsorption effect of around 5 to almost 10 millivolts, and about less than 0.5 absolute % efficiency increase due to these effects. Short circuit current is usually not strongly affected, since you don't have a lot of recombination at this point. But how strong is actually this current being redistributed between top cell, bottom cell, top cell with itself? We can also quantify this now with this model. And I think it's the most interesting quantity is this kind of like relative contribution, so compared to the external absorption, where you can see actually at MPP, the reabsorption accounts for only about 1.5% of your external optical absorption. However, of course, if you go to VOC, where your recombination is much stronger in the top cell, you also have much more emission, and therefore you actually get up to almost 25 or 20% of your external generation. Also interesting to see here, I mean, we saw it already with this kind of like reabsorptances in the optical loss analysis, that the photon recycling currents and the luminescent coupling currents are of quite similar magnitudes. Now, maybe you saw it before. Again, the orange curves are including Shockley-Reed Hall, and we actually see that the curves including Shockley-Reed Hall are higher than the ones with in the radiative limit, which kind of made me scratch my head a bit. But actually, this points at an interesting phenomena that here, in the case with Shockley-Reed Hall, actually current matching was not anymore fulfilled. Like the current in your silicon subcell was actually lower, which meant that you had higher recombination in your top cell because basically your charges couldn't get out, right? Reminds me of the discussion we had yesterday. If luminescence quenching, is it now recombination or is it improved? Yes, if you get your charges better out of your device. So here actually it's kind of both, because you get your charges better out of your top cell through the recombination. So actually, it's interesting to see it kind of be both. Also another, I think, interesting point to mention is it's not only the magnitude of your currents which are redistributed, but also you have to take into account that the profile can actually be different. So if you see here, the blue curve is the external generation, and due to the different angular and spectral characteristics of these two light sources, actually your reabsorption or absorption in general in your silicon device subcell can be quite different, which might actually have an impact between, or may have a difference between your external and internal light charge generation. Just very quickly, last slide. Of course, we always think about how does the internal quantum efficiency affect these effects. On the one hand, you have the recombination junction, which actually, as already kind of hinted before, can increase your emission if your charges can't really recombine with in the top cell with the charges in the bottom cell. But of course, if you have a very bad junction, it doesn't really matter, because usually your performance already degrades so much that it doesn't really matter anymore. Now, if we just look at the IQE in your top cell, of course, here you have the usual effect that you would expect. The lower your IQE, the less emission you have. IQE is sometimes a bit difficult to define, as we already heard, because I mean the lifetime is not really like one number. It depends on the voltage, on the current injection. But in general, you can clearly see that if your IQE goes down, then your photon recycling and luminescent coupling current will very quickly be quenched quite strongly. Okay, this already means I come to my conclusion. So we showed our optical model, which couples coherent and incoherent light. We couple this also to the electronic model of the diffusion model of Sept. This photon recycling and luminescent coupling leads to an increased quasi-Fermi level splitting in both your subcells. Interesting, there's some plots again missing, but okay. Also, it's not always as easy to analyze as one thinks, because of the complex interplay between the recombination mechanisms, the junction, and so on. And just as a quick outlook, I already mentioned in the motivation, the best cells nowadays, they are textured. So this will definitely be one next point that we need to implement in our own model, that we support textures and scattering, as well as tunneling models, which basically can be used to model tunneling junctions, but also intraband tunneling through tunneling oxides and so on. And yeah, with this, I would like to thank our sponsors and be open for questions.
Thank you.